And we are recording. Welcome to the evening of Python coding. I'm very happy that you're here with us. Today we have Jason Gauchi. He's now in Argo and he's doing very important and interesting stuff there, and hopefully they'll tell us more about what they're doing in the future. But for us, he prepared a demo of a library called Network X. He has a lot of experience, and he will describe it much better, all of his experience. So, Jason, present yourself, tell us a little bit more about you, and then tell us a little bit more about the Network X.
Hey everybody. Yeah, my name is Jason Gauchi. I'm at Argo AI, so I'm director of ML infrastructure there, where we're building some really nice software and tooling to make it very easy, very accessible for all the researchers to do what they do best and really make it work at really large scales. So prior to that, I was on the other side of the desk. So I was a researcher I was at Facebook Research. I was at a research kind of area in Apple, and then I was at Google Research, and I was at Lockheed Research. So I've been in research um, for probably 1.5 decades, and really focused on control theory, decision making, and reinforcement learning in these kind of areas. And as you can imagine, all of those companies have a lot of robotics, a lot of decision making. There's auctions in most of those companies in some way, shape, or form. There's bidding. There's choices that have to be made. I've helped out in some way in kind of all of those areas. So I found Network X to be a really awesome library, and I wanted to share it with everybody. And so I felt like many of us, got into programming through video games. We wanted to create these virtual worlds, and partake in them, and we're fascinated. A lot of us are fascinated by games, game theory, um, and just the pattern and keeping people in the zone. And there's something really alluring about all of that. And so I took inspiration from this game called Stellaris to kind of explain Network X in more detail. And so what we're going to do here is we're going to create a Stellaris map, like you see here, which is made up of these solar systems and then these edges telling these aircraft, which solar systems are adjacent to each other. And then we use NetworkX to analyze this map we procedurally generated and give us some insights, right? So folks who are actually in the games industry, what they've told me is that, the hardest part of building any type of game, even a card game, is balancing the content and balancing the gameplay and keeping people sort of in that zone where the game isn't unfair to them, but it's also not so easy to just exploit it and keep it kind of really interesting. So we're going to look at how Network X can shed light on our auto-generated map here. So what we have here is this is the code that's generating that map. I won't go into a lot of detail. It's not particularly relevant, but I'm basically doing a Delano decomposition of a bunch of nodes. And when we're done with all of that, we're taking this graph that we're generating, and we're putting it just into Network X and plotting it. And so this is what we're left with.
Okay, just to
So
tell them what Delano
we
is.
have several different clusters. So there's about 4 by 4 clusters of nodes.
Jason, before running, tell them something about Delano, what it is, a little bit.
Sure. So yeah, I mean, this is off the top of my head, it's hard to remember, but basically, if I remember correctly, it's a kind of wing adding algorithm where when you're done doing a Delano triangulation of a graph like this, you end up see if you notice there's very few thin angles, right? There's very few thin triangles. And so what we've done here is we've taken this sort of cluster of nodes and we've created this nice mesh on top of that, such that all the triangles are, have relatively good angle. There's some code around eliminating triangles that are thin, because there's some cases where there's really no choice, but it tries its best to be really nice. I think there's like a relationship between this and a Voronoi
Yes, it's a subset.
representation.
Yeah, yeah, it's a dual, it's a duality. But what
Oh,
you're
it's the dual of the Voronoi.
yes,
Okay.
yes, yes, yes. So won't go into details, but basically, I'll simplify whatever you're saying even more. But Delano triangulation is kind of like the nicest way to create triangles from a bunch of points.
Hmm.
It's kind of the nicest way to connect them, so the triangles will be as not as thin, so they won't be any very thin. If you connect some of those points, like here, number 62 and 66, if you look at number 62 and 66, you will create a triangle that is kind of like very thin. So Delanoy avoids it. So
Sure. If I can
what.
jump in too, shot in the dark here. Is that triangle problem you just described? Is that all related to like the Steiner tree problem? Or is that just?
I don't know about that. A Voronoi diagram is such that you have lines where the nearest neighbor changes. So, for example, if you look at just 3 and 4, this point right here, where can you everyone see my mouse?
Yeah, I see.
Okay, good, cool. So this point right here is closer to 3 than to 4. And then if I go this way, now it switches over. Now 4 is the closest. And so right there at that boundary where the closest point changes, you would draw an edge. And if you do that over the entire graph, what you're left with is a Bernoulli diagram. And so this Delano triangulation is the dual of that
Gotcha.
graph. Yeah.
Okay, then that's not related.
What you're seeing here is actually I've redacted some of the triangles that were too thin just with a high pass filter. And so that gives us this nice graph where there's some choke points like right here. And so you can imagine if you're playing some type of strategy game, you'd want things like this to make the game interesting. Like you see this in Risk in between the continents, right? So this will, if you were to run this on your own, every time you'd run it, you could change the random seed right there. Every time you change the seed and run it, you'll get a different graph. But it'll always have this nice shape to it.
So the Delano is a function that NetworkX provides you, or did you bring it from some other library?
Yeah, so that came from SciPy. What NetworkX has done so far has been just to render this graph.
Okay.
So it has a it's connected to matplotlib, and so I've just called nx.drawNetwork, and I've gotten this network here.
So what you
Yeah,
did is you just dropped a bunch of random points in space and then created triangles to create a mesh and then plotted it so far, correct?
right. That's correct.
Good.
And so getting back to the inspiration here, right? I mean, we can generate a lot of these maps, but some of them might not be very fun, right, to play on, depending on whatever game you're making. And so you can imagine a situation where you implement your game and you play maybe an AI or a friend in this game, and then you go by hand and say, this was fun, this was not fun, this map was fun, this map was not fun. Or maybe you don't even play the game, but you just use your human common sense reasoning to say which maps are fun and not fun. And so you've gone through and labeled these. And now what you want to do is build some kind of classifier, which would take one of these maps and tell you how fun it is. So you could just, generate a bunch of these and then keep the most fun ones, right? And so if you're going to do anything like that, you need to know the features, the essence of this graph, right? And so there's a bunch of different techniques which are really important here. I've talked to one of the founders of ThinkFun, and they do a lot of this when they're inventing new kind of board games and card games. They're really looking at what are the sort of essence, the features of whether it's a graph or whether it's some spatial representation of something. So in this case, one of the things we can do is the minimum spanning tree. And so this is going to give you a tree, so that's a graph with no cycles, such that you've occupied the minimum distance. right? And so in this case, we don't have a weighted graph, so it's a little bit less interesting, but you see you end up with a nice little spanning tree. You have a tree that now covers every node.
This tree,
Yeah,
you
go
can
ahead.
start from one node that is the root and you reach every other point in the graph. Correct? This is
Right. Yeah. I mean, any node, could be a root in this case, but you're right. Yeah, you can from any node you can reach any other node um, using only exactly one way.
good. So this is like, so it removes all sorts of redundancies and it makes sure that this is this spanning tree. Remind me, this will be the easiest path between each two nodes or only from one node to every other? Like,
Yeah, so the minimum spanning tree is going to be, it's mainly intended for weighted graphs, right? Which Network X fully supports. And the minimum spanning tree is the tree that covers all the nodes and has the least sum of the weights. In this case, all the weights are one. So any tree that covers all the nodes is going to be a minimum spanning tree.
so to simplify it even further, if the weights are the size of the connecting
Or like the
edge,
distance or something.
yeah.
Yeah.
So it will be like the minimum distance between all the places, kind
Right.
of.
Right. Yep. Yep.
And you did it with
Um,
one command, correct?
Yeah, and the other thing about Network X is, under the hood, I'm assuming, I mean, I haven't verified this, but I'm assuming under the hood it's all C++, or maybe it's written in NumPy, but under the hood, when you get down to the operations, they're all, being done in C++ or insanely fast. So I mean, like, something like this runs, in an instant. You probably couldn't even time it. It's so fast. Um, so another thing you might want to do is get the chain decomposition. So I'm plotting here just the biggest chain.
What's the
And so
chain
this is,
decomposition?
yeah, chain decomposition is where you find the largest cycle in the graph, and then you sort of redact that and then find the next largest cycle. And you just keep doing that until there's nothing really left for you to look at. So you'd imagine there'd be a bunch of chains here that are just of with one edge in them, right? But here, this is one really long cycle in the graph. And so you could imagine maybe graphs that have a really long chain, could be good or bad, just depending on the gameplay. Maybe a longer chain means the game just takes longer to finish, and depending on how you feel about your current gameplay, you might want to use that as one of your features,
So this
right?
is the original graph, and I see many nodes disappeared. If you can show the original one, I saw like all
Right.
the
So
60s up there don't exist anymore. Not the spanning tree, but even so.
Right.
Based
So this is one of the largest circuits that you can make in the graph, but it's not like a traveling salesman or something. It doesn't cover every node. It's just a very large circuit.
so this is not an NP hard problem, correct? This is computable in polynomial
Um,
time.
I believe that's correct. Finding the largest, yeah, this is really stretching my
Okay, I
undergrad CS theory,
apologize.
but no, it's fine. I mean, I think finding the largest cycle in a graph, I believe you can do that in polynomial time. But either way, definitely the documentation will tell you. Actually, that's one thing I should mention. Network X is very explicit about telling you
So
what functions are NP complete.
So can you show us,
Um,
for example, can you just bring a web page and show us like the documentation and go through it
uh,
while we do
yeah,
it?
sure.
Just to give an example of like for people who want to study it or and
There we go.
and can you make it bigger for
So
us for a sec?
sure. Yeah, so Network X has phenomenal documentation. They have a whole section called algorithms. This is where the most fun is.
Oh my
And
God, how many?
they have everything. I mean, they got absolutely everything. It's like mind blowing. And I can't remember exactly which one I saw, but there was one where it definitely warned you that it was NP complete.
So let's try traveling
Um,
salesman. Do they have it here? I assume.
sure, traversal maybe, depth first search, breadth first search.
This is beautiful. Yeah, no travel.
Yeah, I'm sure. I'm sure they. Here we can do this. Everyone should be using Brave, by the way. Brave browser. It's phenomenal. Yeah, here we go. So it's under the. I guess they have an approximate traveling salesman,
Yeah,
maybe. But
that's
in
NP
this
hard.
approximation,
They won't be able to do the one the proper one. It's the NP hard. For
yeah,
people.
I mean, it would be it would only work for small graphs,
Yeah.
right? If they did
For,
the proper one,
so
they would basically have to try every permutation.
yeah. So for the very first beginners who actually come here and we're talking something like NP hard, can you tell them a little bit more about what NP hard means and what polynomial time means and why is it related to graphs?
Yeah, sure. So, yeah, again, I mean, I'm going to be people who have just finished undergrad will do a much better job at this, but I'll try my best. So, um,
In simple words.
yeah, I mean, ostensibly, I mean, anything that's in the class of P can be solved in polynomial time, which means, given the number of entries, in this case, let's say it could be the number of nodes or number of edges, maybe it takes the computer that squared or that cubed or that to the fourth to solve that problem. And generally, even if the exponent is large, if it's a constant, you're usually okay. Very rarely are you going to see an algorithm that's more than n to the fourth or n to the sixth. Um, when something becomes to the nth power, like n to the m power, or something like that, where m now is unbounded, so that the thing you're raising it to is unbounded. That's when you start running into real trouble, right? And so for something like traveling salesman, um, you would have to try all possible permutations. So that might even be that might be n factorial or something. But either way, it would be a very extremely expensive algorithm that you'd only want to run on very tiny graphs.
Yeah. In a nutshell, if you ever see the word NP hard, this means this problem will take all the computers in in the world, and it still take many years to solve it properly for a large set of nodes, like let's say even 1,000. So
And so that's where these approximations come in, right?
yes.
Because there's a bunch of people have analyzed this and they've found that there are certain techniques that you can follow that give you 99% or you have some nice bounds of how close you are to the perfect answer, and they'll run in polynomial time.
Yeah, and sometimes they actually find a perfect answer, but you can never prove it because sometimes those problems you you cannot compute what the real answer is. It's
Yeah, like so simulated annealing is a good example. So the way simulated annealing works is traveling, actually, let me take a step back. Traveling salesman is this problem of how can you visit every node in the graph and take the minimum amount of total time, right? So imagine you're delivering Amazon packages or something. How do you deliver, like whose house do you visit in which order such that you've delivered all the packages in the least number of miles, right?
and return to your home base and
And return to the home base,
and
that's true.
visit only place only once.
Correct. Yeah. So simulated annealing is a very simple algorithm. What it does is it starts with just a random circuit, right? A random, you randomly visit all these houses and then return back. Then what it does is it tries swapping two of the houses in that list, and it sees if that new result is better. If it's better, it takes it. And if it's not better, there's some probability it takes it anyways. And that's the annealing. So over time, in the beginning, you're just random and you're also just swapping and randomly taking those. But over time, you start annealing that randomness and you start only taking swaps that are better. And there's a bunch of really nice mathematical properties when you follow that. So you do that, and at the end, you're only taking a swap if it's strictly better. And so you run that for a while, and you'll get something that, again, it's all based on statistics and probability. That you can invent a situation where this gives you the worst possible answer. Like it's theoretically possible, but it's extremely unlikely. And so the likelihood you get the perfect answer is way higher than that, right?
So NetworkX has a bunch of those algorithms already built in that you don't have to write them.
Exactly. Totally built in. You can just benefit from them.
Good, good, good. So let's go back to the NetworkX demo and see what else can you show us.
Yeah, sure. So here's NetworkX getting all of the bridges. So a bridge is an edge that breaks the graph into two if you were to remove it. So let's look at the original graph here. So there's very few bridges, right? I mean, imagine if I remove this edge, that breaks these two
17,
nodes
30?
from. That's right. That breaks these two nodes from being directly connected, but you can still get to 13 just by going around here, right? And so we didn't actually break the graph into two components, right? And so when I look at the call bridges, actually all I get are these two. Now, it might be that, again, going back to the inspiration here, it might be that the game that you're designing or trying to invent, can't tolerate any bridges. Like maybe you have to be able to eliminate any one edge and still be able to visit every node. And so what you would do is, you would run this bridges, and if anything came up, you would throw this graph out, you would adjust that random seed, and you would keep trying, right? But this is a way in just one call, you get all the bridges, which is really nice. I'll go through just a bunch of, definitely take a look at the NetworkX tutorial. The reference I just showed. It has a lot of really cool stuff. So I'll just go through some of these. This is a measure of closeness. NetworkX has a ton of these different ones. I picked, centrality is the thing we're measuring, but closeness is one way to measure centrality. And so I don't remember off the top of my head how closeness works. There's one that uses eigenvectors. I think that's a different one. I think there's one actually called eigencentrality. But this more or less, just looking at it, it kind of does what we expect, right? Like this one's way over here, it got a value of 0.11. This one's right in the center, it got a value of double that. Right, and so you can imagine, if you had a lot of gameplays, you could use this number as a feature, and maybe you learn something like people who start with a high centrality just always win, and so that's a problem. And so maybe if you start, maybe everyone should start at a node, like all the players in your game should start at a node with the same centrality, to keep it balanced, right? Here we're getting into flow. So flow is the idea where we think of a graph as, channels where we can send electricity or information or water or something over that graph. And so we're interested in things like what's the maximum flow, how much can I send from one node to the other? And so we're going to set an attribute here. So nodes and edges in NetworkX can have attributes, and they can be anything you want. But if you want to do max flow, the attribute is called capacity by default. So we're going to set this attribute on each of the edges, and we're going to say they have a capacity of 1. So each of these edges can hold 1 unit of, let's say, water or information. Now we're going to go and see what's the max flow from node 0 to node 73. And it looks something like this. So here's node 0, here's node 73, and we can only send 1 unit of information from this node to this node, which makes sense because this was a bridge, if you remember from earlier. So this is the bottleneck right here. Although I guess maybe there's one here too. Maybe they're both bridges actually. Again, using the draw function is very customizable. I was able to draw labels on the edges, and NetworkX handles all of that for me, so I don't have to draw any of that by hand. Here's a more interesting flow. So now I chose these nodes here, and as you can see, there's actually 2 paths. And so I can actually send 2 units of information from one of these nodes to the other at the same time. any questions about this? Does this make sense?
Yeah, this is beautiful.
Yeah, this is super fun. And so again, going back to the game thing, I mean, as this game maybe gets more complex, you would maybe you would learn actually, drawing some inspiration from SimCity. This is actually how SimCity worked, the original SimCity. Um, and I'm totally drawing a blank. Who's the person who founded Maxis, who made SimCity? Totally
Sid
doing.
Meier?
Yeah, that person made Civilization.
Sid Meier's? What do you mean Sin City?
What?
Sid Meier's has made Civilization.
Will Wright. So Will Wright actually used this exact algorithm when deciding how much traffic there should be. So the way SimCity worked, the original, was every cycle of the game, Will would pick two random buildings and then find the max flow between them. And then he would add that number. So in this case, each of these edges would get incremented by one. And then to keep it a probability distribution graph, you would divide the whole graph by a number so that the sum of the edges was one. And so every single tick, you can imagine picking two random nodes, running this max flow, and then adjusting this graph. And if you do this enough times, this one edge, let's say, that's connecting two popular places is going to get a big number. And that's actually how the traffic worked in SimCity. So with Network X, you could write that part of SimCity like almost trivially, which is really cool.
Whoa.
We just got some questions in the chat. First,
Cool. I'm actually all done. So we'll jump straight into answering some questions.
I see right there.
Read the question, Silas. And if so,
First one is, do you recommend using a graph database like Neo4j when playing with this library?
Yeah, that's a good question. So, okay, maybe the more general thing is graph databases are good for making graph queries. Like you could say that Network X, a lot of the things you're doing in Network X are graphical queries. And so with Network X, everything has to be stored in memory. So eventually you're going to reach a point where that breaks down. Maybe the graphs are too big, or they're just extremely sparse. So there's some issue where Network X isn't going to be what you want. And there, a graph database would work great. I don't exactly know what Neo4j, what the relative features are. Like I don't know if MaxFlow is a thing Neo4j can do, to be totally honest. But yeah, you would use Network X when you can fit everything in RAM. I don't know how it plays with Dask, and these other things that do the distributed NumPy. But either way, Neo4j is an awesome graph database for storing really, really big graphs. So just continuing with this example, each graph is small. Now you might have thousands and thousands of simulations or real life playthroughs that you want to analyze, but each one is pretty small. And so I would probably just stuff everything into something simple like a MySQL database or something. Because I know I could just pull a single game up and then do a bunch of analysis. But yeah, I mean, you could maybe you could use Neo4j to do really like a meta level analysis over the different space of types of games you could create. Yeah, that's a good question.
More questions, Silas, in the chat?
Next one, what is the important to calculate the max flow? I assume it means why is it important to calculate the max flow?
Oh yeah, so I mean, I talked about it for the game. In this case, if two nodes have a lot of max flow, that means it's very easy for one to get to the other. And so that might mean if you're doing something like Stellaris, that's a node that's very vulnerable, that it's easy to attack. So for example, if you have two players who are starting on nodes that have a high max flow to each other, that might be a bad situation. It might make the game short or it might make the game unfair those two players just always will end up clashing, and then they'll both end up weak, and then the third player will just dominate, right? So these are all things that you would calculate when you're trying to balance the game. I used Maxflow recently um, for this. There was this auction situation where we were interested in auctions that involved logistics. So, for example, let's say you bid 14 for this commodity, and I bid 13, but it's going to cost twice as much to ship this commodity to me. And so, even though I bid 13, it's actually the or sorry, maybe I got that backwards. Even though I bid 14, I bid more. The shipping costs are so much higher. They want to give it to the other person. And so there, to do that sort of matching of buyers and sellers in real time, we use Maxflow to try and match up the best buyers with the best sellers. So there's a lot of different applications of Maxflow.
Interesting. So you were talking about game situations, but let's talk about real life situations. Let's say I'm an architect or some sort of engineer in the city. How can those algorithms be useful? Just throw a wild example, just so people to understand what the power of this is.
Yeah, I mean, we talked about SimCity, right? But you could imagine doing that in real life, right? You can
Like
imagine
Austin
seeing
traffic.
what is the centrality of the different intersections in Austin, right? Um, I think that there's no end to the cool stuff you can do there. Um, yeah, I think that would be actually super interesting. I mean, taking some data out of OpenStreetMap and then doing some of these computations on it. I think maybe you could be your own real estate agent or something.
Yeah.
Be an investor, a real estate investor.
Yeah. I won't ask question. I know you work in Argo, and this stuff is probably very useful for what you do. So since you probably don't expose exactly what you're doing there, but I won't ask the question. But people might get an idea of by just looking at this demo and understanding what the potential is. Like this is how
Yeah,
important those
totally.
are.
I think that one thing that's really interesting is um, you're seeing now a lot of everyone's really hyped up on deep learning, and deep learning is awesome. I mean, it's great. And what you're seeing now is you can actually do function approximation on something that can be really complicated. So, for example, you can have something like a Max Flow or a traveling salesman or any of these like sort of operations research, like different type of linear solvers, right? And you can train neural nets for a particular domain to try to accelerate that solution, right? So it might be that the problem is NP complete, but every graph I'm interested in has a certain structure, and if I know that it has that structure, I can then create a polynomial solution, right? Or if it's still a approximation, it's so much better now, right? And so um, you're starting to see this convergence of the deep learning, the function approximation world with the symbolic world, which I think is really exciting.
Interesting. I would love to get personal questions from the audience. Please, if you're not shy, then please unmute yourself, ask questions. Network X related. I know people are not like.
Or anything. Doesn't have to be network X related.
Well, we
You
can
can
keep
ask any.
anything
I will
after the
give
recording.
I will give an answer to everything. I don't know if it will be a good one, but it will be an honest one. So.
Is there a way you can do like 3D? Like Stellaris, it shouldn't be on a flat plane. I don't know, or like some cities aren't so flat.
Yeah, it's a good call out. So Network X supports any dimension. The way Network X works, it's designed for just adjacency graphs. So it doesn't necessarily concern itself with where is this point, right? In fact, even just taking a graph without any spatial information and drawing it appropriately is itself an NP hard problem. And Network X has a bunch of heuristics, even just to draw a graph, right? Like imagine, your graph of your social graph, your graph of your friends, right? Network X can actually draw that in a way where it looks pleasing, right? Um, but yeah, to your point, so you can give any dimension coordinates you want to those nodes, or even like 17-dimensional nodes, and as long as you specify sort of the right distances. So you would have to by hand tell Network X all of the distances between all the points. So as far as I know, and there might be something in there I just haven't seen yet, but as far as I know, like it's up to you to like calculate the Euclidean all those times and give Network X all the edge weights. Because Network X is not assuming any type of Euclidean space or anything like that. Yeah, it's a good question. Oh, and actually, to answer your question about Stellaris, I mean, this is I'm gonna go a little rant here, but this whole like 3D versus 2D is super interesting. It turns out that a lot of games actually work way better in 2D, just as games. And so even though it's kind of silly to think of the universe as like this sheet of paper, but I remember when Dwarf Fortress went 3D, and it really kind of the user experience really suffered. One of the challenges there was the game, original Dwarf Fortress was designed where as you move to the right, the game gets harder. And now that it was 3D, they couldn't really do that anymore. I think they've tried to make it so that as you dig further down, it gets harder, but it didn't really work the same way. So I think the game devs probably made a good move there, keeping it 2D. But you're right, it is on its face a little bit silly.
Now I have to play the game.
It's a great game. Yeah. The only thing is, you might kind of look at the clock and say, how's it 4 a.m. already?
Oh yeah, oh I know those games. Don't remind. Ouch, ouch.
Yeah. Look, I know people have played the board game Twilight Struggle, but that's a similar thing, or Diplomacy or something, where you're playing this game and all of a sudden you look around and it's like, oh, I've made like 3 pizzas for everybody, and we're still here.
Yeah, I played Twilight Struggle as well. Yes.
Yeah.
This is amazing. It's like so many games, so many graphs. Someone was asking something in the chat. I couldn't figure it out. Silas, can you pull it out, or the person who asked the question, can you just ask?
Oh, sorry, I'm missing. I didn't scroll down. Is there there's other algorithms like genetic algorithm, ant colony algorithm to solve these kinds of problems? Talking about the other optimization.
Yeah, I mean, I could definitely talk everyone's ear off on black box optimization, right? I think that's genetic algorithms. There's ant colony. There's simulated annealing. There's Bayesian optimization. There's a whole bunch like Gaussian processes. There's a ton of different methods. Really, really fascinating stuff. There actually is another here. I guess I'll share this as well. There is another really great library called Nevergrad. And Nevergrad is a gradient-free optimizer. So, folks out there who have a ML background, typically, you have some neural network, you calculate a score, I expect the answer to be 2, the answer is actually 3, and so now you have a difference of 1, and you what's called backpropagate that difference. So it's a little complicated, but effectively you find roughly what the gradient is at each of these steps in this process, and then based on your error, you either amplify that or invert it. There's times you can't really do that. There's problems that are not differentiable. And so for that, you have Nevergrad. And this is I love this library. I know a lot of the folks who wrote it, and I'm a big fan. It's got a lot of great stuff. So if you're doing some kind of optimization, like imagine, you're trying to do split testing with people, or you're doing some kind of testing where you don't have a good feature space. It's really a black box, and you're trying just different inputs and trying to get the biggest output. This is a really cool library for that.
Whoa, I'm amazed. There was another question later on. I see them popping up, but
Yeah.
Silas.
How are the hooks between network X and something Bayesian like pi MC? I don't understand that one.
Yeah. So PyMC is this Markov chain Monte Carlo library. So that is I'm trying to figure out how far in the rabbit hole to go there, right? But basically, MCMC and related stuff is all about kind of sampling and then using sort of different types of sampling methods to estimate distributions. So it's a good question. I don't think there's a concept of, I guess, like a quantum graph or a graph with edges that are drawn from random numbers. So yeah, I would have to say that I don't think Network X plays really nicely with something like that. I think you would have to sample, if you did have so just to bring this back down to earth, right? Imagine if you have a social graph and some people are clearly friends, some people clearly have blocked each other, and then for everyone else, you don't really know. It's like there's some probability they're friends, but you're not sure yet. So that would be an example of you have this huge probabilistic graph, and so you could sample. So you could go through all the edges, flip a coin, use the probabilities of bias, and now you created a hypothetical graph of people who could be friends. And then you could take a sample of that Bayesian graph and put it in Network X. But I don't think there's any real tight integration or anything like that. You'd have to write all of that yourself. Yeah.
Please, if someone has more questions, they can ask them
Any other
directly.
questions? Yeah. If people want to ask about machine learning in general or anything optimization related, just go for it. You want to know how a self-driving car works? I won't give away any IP, but I could kind of go into that.
We're on the hook for that. We'll get you to talk about it
Okay,
another
yeah,
time. It's like this is a whole full discussion without giving away any IP. We want you back to tell us more about this stuff. This is exciting. But
sure.
but if anyone has more general questions, Python related, even things like how to start with machine learning, go ahead and ask.
Sure. Yeah. If you want to know how to start programming, I have a podcast called Programming Throwdown.
Oh, can you put us a link? Can you give us a link?
Somebody jumping in to ask something. Feel free to ask something on the voice.
Oh, yeah, go ahead. Here, I'll put a link to the podcast. Feel free to check it out, especially if you know folks who are beginners.
You can share the screen even. It's okay.
Hello.
Oh, go ahead.
I asked the question in the chat about, especially because you work with self-driving cars, how would you go about labeling human opinions? Because there's no definite correct label there. You have to get a consensus of people. And thoughts about that problem. You talked about it when you're talking about labeling networks by how fun they would be to play. You have to, define what fun is, and then you'd have to get a sample of people to kind of like label it accordingly. So
right. Yeah. Phenomenal question. Really, really good question.
Okay. Before you run into this question, you're showing us AI for code with Ron Yahav.
Okay. So this is Programming Throwdown. So it's a podcast. Most of the people are listening to it on iTunes, but it's got all these options. It's even the RSS feed. You can put it into any podcatcher you want. And yeah, check this out. We interview a bunch of folks from all over the world. This is a gentleman from Israel talking about AI code generation tools, which is really, really neat.
You're one of the interviewers?
I beg your pardon?
You are one of the people involved in doing this?
Oh, right. I'm the co-host.
Thank you.
So Patrick and myself host this, and we push. We do an episode every 2 weeks.
Okay. So. Can you zoom it in so people can see exactly to give you some? This is being recorded, so please join the podcast, and the link is.
It's programmingthrowdown.com.
Thank you. So,
and if you type programming into your podcatcher, your podcast app, we used to be #1 for programming, the word programming. We didn't do any SEO, but we just got lucky, I guess. But We've also been doing the podcast for a long time, since 2011.
Whoa.
Yeah, but yeah, check it out. Okay, so the question is fascinating. The question was, just to recap, how do you get clean labels? I think that's the more general question. So, for some things it's obvious, like if you have a picture and if there's a stop sign in the picture, and you want someone to draw a box around the stop sign, you could very clearly tell, this person drew it correctly or not. And you might farm that same image out to 3 people and get 3 results back, and maybe you choose the smallest one, right? There might be some tricks there, but more or less people are going to box the stop sign and you're good, right? That's supervised learning, right? That's learning with very nice supervision, right? It becomes a challenge when you're doing optimization, which is different than supervised learning, right? In the case of optimization, you want to be the best. And unless you already have a perfect, whatever it is, player or driver, then you can't do supervised learning, because anyone who gives you any data is going to be not the best. They're going to have their own errors, right? So for optimization, you still have features, but it's not just a matter of blindly just taking every sample you get. So optimization is tricky. That's what makes it hard, but it also makes it really fun. There's a bunch of different algorithms to help with that. But I think an easy way to say it is the simplest way is to do it purely democratically. So if someone says the game is fun, then you say, if they gave it a 10 out of 10, then you say the game is 10 out of 10. Now that's one sample. So if you have a very similar game and everyone hated it, you have, let's say, 100 samples of the latter, then your algorithm will converge to saying that that's not fun. And so with enough samples, you can do imitation learning for something like deciding if the game is fun or not. It still doesn't help you make the most fun game. But even for that, you could just generate a lot of games and then pick one that has a high enough score. For self-driving car, right, it's a little bit different because it's a sequential problem, right? It's not like you're doing this one step, generate a game, and then this one reward, this one value, this one utility, right? It's like this constant control loop. And it could be, I mean, in fact, it is. If you were to look at any situations out on the road, they're a product of a lot of things that happened in the past, right? And so that's where it starts to get really, really complicated. Even look at chess, right? So chess is also a sequential game, and if you play a bot in chess, maybe you are ranked around, let's say, 1200, and you play a bot that's ranked 1200. You might each win half the games, and so the ranking of the bot is accurate, but you won't play the same, almost guaranteed, right? The bot won't play like a 1200 rated player. What it will actually do is it'll play like a 2000 rated player half the time, and a 400 rated player every now and then. And that's because it's very hard to imitate a human's behavior when they are doing any type of search or anything that involves many steps. It's very hard to combine imitation with something like that, because you have to kind of reverse engineer what the person was thinking, but all you have is their final decision. And so that's why all of these chess programs, if you go on Chess or chess.com or anything, they're going to play a way that feels kind of unorthodox, even if they're of equal strength as you. So that's cutting edge stuff, right? It's not an impossible problem. Like, with enough data, you could solve it. It's just very, very, very hard. But one awesome thing about research and AI is that things that are impossible just inevitably become hurdles that then you overcome, and then they become such small hurdles, you just step over them, and then they just become nothing, and you're just not even there anymore. That's what I've noticed in all these years of being in AI.
Thanks for that answer. That was really interesting about how it plays actually at a mix of 1200 and 400.
Sure. Yeah. Thanks for the question.
Any other questions?
Actually, I opened up the chat. So somebody asked, tell us about the stuff you were researching in previous roles. Yeah, it's a good question. Actually, I can share. So the nice thing, a lot of the work is public because it's open research. So at Facebook, I worked on this thing called Reagent, which is a reinforcement learning platform. And we have a little white paper here. You can go and check out. It used to be called Horizon, but then the VR team stole our name. So one of the unfortunate things about working at Facebook, especially in research, is that it's a huge company and you're not a real product, so it's easy for someone to poach your name. But this was a way to solve a problem that is now becoming going under the name offline reinforcement learning. Back then, it wasn't really called that. We were really the first platform that did that really well, and so this is everyone knows about AlphaGo. I mean, I worked on a lot of that stuff too. In AlphaGo, the machine is playing itself in real time, so it sees a mistake, it fixes it, and it's ready to go again. In the real world, you can't really do that. You can't say, I'm going to, fly this space shuttle, and every now and then, the space shuttle will have some catastrophic failure. But after crashing millions of shuttles, at the end, I'm going to have an awesome one. Right? It's just not practical, right? So you need something that can take much more trusted, slow but steady steps in the right direction. What you have on the positive side is effectively unlimited data. And so, this is a very different problem to standard RL. And so we came up with a set of algorithms that did this really well. So that's what I did at Facebook. At Google, I worked on this thing called Sybil, which I'm sure does not exist anymore, but we can still find it on the internet. And Sybil was a really large-scale machine learning, and this powered a lot of Google's machine learning. At one point, we were training the model that generated all the suggestions, like when you go to YouTube. Actually, let's not do that. I mean, my YouTube should be tame. It takes a lot of my son playing Minecraft and stuff, but I don't know what's going to come up there. But actually, we could do this in incognito. Oh, that's a different window. Anyways,
just tell us.
But when you go to YouTube.com, you get all these videos, and that's a set of recommendations, right? You click one of those videos, and you get the recommended video. Because you watch this video, here's some ones you think you're going to like. All of that, circa 2012, 2013, was all powered by Sybil. And so Sybil was a machine learning algorithm that ran on tens of thousands of machines. And to make it work, we actually we used parallel coordinate descent. We didn't use gradient descent because we just couldn't compute gradients on that many features. We actually had something like 20 features for every person on Earth or something. We had like 100 billion features. It's some insane number. And that model kind of generated all the recommendations for all of YouTube. So yeah, that's kind of what I've been up to.
Good. Quite amazing.
I've got a whole question. I've got a question for you.
Sure.
Jason, this is very much a less algorithmic question, but it's to do with the algorithms. estimates by people as closely involved in the technology as yourself as to when autonomous cars would be a viable product have constantly been optimistic. They've constantly been put back.
Right. Not my estimate, for sure.
Well, that's why I was asking you. Your estimate's obviously dead on to the day, maybe the afternoon. What was your estimate of when that day will be? And why was everybody else making estimates that were so by not by months but by years way off?
Sure.
Whoa.
Yeah, I can give my take on this. I mean, this is a Jupiter level gravity on this question, right? But okay, so I remember telling everybody that the self-driving car thing was total BS, and the reason is because it is a optimization problem. It's not a supervised learning problem, right? And so people grossly underestimated the optimization part. They thought, well, I have these cameras, I can see everything that a person can see. I know there's signs here, I know there's people here. I have occlusions, but I can just remember. I saw a person go around the street, so I expect them to come on the other side. Right? They were thinking about all of these things, and they said, well, eventually, I'll solve all of these supervised problems, and I'll be done. The problem is that driving is an optimization, right? You're trying to trade a lot of different things off, right? For example, there's a person walking in the road, and this sounds a little bit dark, but the reality is you're kind of willing to like run over a person if they jump in front of your car, right? I mean, most of us don't even think about that, right? So it's like you're going 40 miles an hour and there's a sidewalk. That person could just jump in front of the car, and you're kind of just saying there's kind of an agreement we have as a community that we're just going to drive the speed limit, and if a person jumps in front of your car, then you're just going to hit them, right? So that's an actual like decision that we all made. I'm not saying that we all voted on it or anything, but as a society, we kind of came to that agreement that cars will go, 40 miles an hour on streets with sidewalks, right? And I'm sure like some number of people, maybe someone passes out, they have a heart attack, or maybe they're on drugs, or who knows? But there's some number of people, in this country of 300 some odd million people who get hit by cars because of that, right? And so driving is an optimization problem. Everything from trading off comfort with where you go on the road, with how fast you want to go, with how you negotiate with the other drivers. So, for example, you might see somebody who looks a little jumpy coming, from the side, and your response is actually to accelerate, because you know that if I accelerate, I'm going to signal to this person that I'm not slowing down. And by accelerating, you are telling that person, don't even try to get into my lane. And because of that, they don't try it. And because of that, you're safe. And a self-driving car might slow down, and then that person might get mixed signals. And then now you have this hysteresis. You have this like who goes now problem, right? So all of that, the economics, the philosophy. I mean, we joke about like the trolley problem. Like you hit like 2 jugs of milk, or like, a bacon sandwich or something. I mean, but that's not really it. I mean, it's really all those other things that are happening all the time, and we don't really think about it. So the optimization problem is nowhere near being solved. I think that there's also problems around out of band situations. Like, what do you do on Halloween? Right? Like on Halloween, it's like all these people are wearing masks, and you might have not trained your model on, Frankenstein or whatever, right? So there's always out of bound issues. I guess I'll just leave it at this. Like level 3 autonomy, so like what Tesla has, where you can take over the steering wheel, and level 4 autonomy, where there's nobody in the car, are 2 totally different problems.
Yeah.
And the idea that like you will eventually get to level 4 by doing a level 3 really well, it's kind of like saying, if enough, people write assembly, you'll eventually write a C++ compiler in assembly, and then you can write C++. Like, you kind of have to go into it wanting to write the C++ compiler. Like, it doesn't just happen by accident.
Okay, and it sounds like it's very different from other problems then, because the delay from the earliest predictions, I mean, credible predictions in the sense that the people were credible in their professional lives anyway, to the present day where we still don't have it, has been probably longer than it's been under development. It's like a government project in a third world country.
Yeah, well,
Or
yeah, I
doing
mean,
the highways.
we joke about how, my parents, my grandparents are both kind of in they do kind of science stuff. And we kind of joke that, people in the 60s, the brightest minds were putting a person on the moon, and now the brightest minds are trying to get you to buy a Toyota, on Google. But the reality is Google had a bunch of super smart people working on self-driving since maybe 2009 or something, right? And they are incredibly brilliant. They're giving it 110%. They have tons of resources, effectively infinite money, and compute resources. And so the problem was just underestimated. I mean, not even it gets back to our NP complete, right? The problem is in a totally different domain than people thought. And so, even Google can't do, traveling salesmen on a really large graph, because it's an NP hard problem, right? And so you have to really rethink a lot of the stuff. I feel like we're getting to the point now where I think level 4 autonomy in very, specific environments is achievable.
Yeah, and a separate but related question is, I've heard that Tesla is the only company that's using solely cameras to do the sensing, whereas others, people are using LiDAR and other technologies as well. Now, what convinced, I guess, Elon Musk that was the best way to go and was possible? Because other people seem to have plumbed on LiDAR being a necessity.
I've seen Elon speak. I can't speak for him, but the argument is a human one, right? He says, look, humans don't have active sensors spinning above our forehead or anything. I think the problem is, again, an out of bound problem. So, if I see, I have a massive common sense reasoning database that's as old as Adam and Eve, right? A lot of it is genetic. It's not even learned, right? And these neural networks have to start from scratch every time, right? So it's different. I think that we all have sort of a communal understanding. The car was designed around a bunch of communal gnosis that we've all had as a society, right? And so these are all things the neural network doesn't have. I think on top of that, if you look at the utility is very hard to compute, right? So look at the example I just gave with the 40-mile-an-hour thing, right? So we've decided that there's more utility in driving 40 miles an hour with the epsilon, the one in a million chance that someone falls into the street. We've decided as a society that that's the way we're going to go forward, right? How do you put that into a car, right? And then let's say you do put it into a car, and let's say the car drives 1,000,000 miles and then hits somebody, right? That's what happened with Uber. And then the Uber ATG car hit someone in the middle of the night who biked into or walked maybe into the street at night, and so that probably happens every hour in America, right? But Uber did it once, and then that was really the straw that broke their back completely, right? They sold that to Aurora, right? So with a LiDAR, you can use simple algebra and geometry to not kill anybody. Now, you might not have the most pleasant ride, right? But you can do a lot with engineering if you have a LiDAR.
Yeah. Okay, I've said enough. Thanks very much. I appreciate it.
Sure.
Andrew, your questions are remarkable. Thank you for the conversation. Just to make sure, Jason, this is all being recorded. This is still okay. I don't have to cut the recording or anything afterwards. You didn't say anything out of bounds.
No, I mean I think that's fine.
Good. It's not related to Network X, but I do have something about chess, and maybe it's an answer to Andrew. So you were giving chess as an example before of AI, but I'm actually giving. I work on disease models. So my question is very similar to what Andrew was asking, but I asked about disease models. When will disease models become viable, where you actually can replace your doctor with a cell phone or something like this? So this is far less solvable than the problems you have with driverless cars. But the question is when it will happen. So I was looking at chess. Chess took about 50 years since the invention of the first program to the point that Kasparov won. So it takes about 40 something years when the computer became the best chess player around. And it's still arguable, but generally it's acceptable now. With driverless cars, this is my second example. The initial experiment started around the 70s, like in the 70s, a car driving between two lanes. Now we have this technology in some of the cars regularly built. And when you commercialized, I think it was 3 years ago, 2 years ago, so Google sold it, and it's now becoming a commercial company. This means that they're getting closer. So the getting back to chess, the question was at some point there was a chess master called Levy. You can actually find this in Wikipedia. And he was betting against him winning against the computer in the next, I think it was a year or something like that. So he made a bet for a certain number of money, and he did win. Later on, a few years later, he would say, I will not make this bet again because technology was advancing so fast. And indeed, the computer became much better. The same thing, I believe, will happen with us with driverless cars. So and when I ask the similar question to what Andrew you asked Jason, when I asked it several of the healthcare people and people who work with computers, generally you can see the people who work with computers always tell you how unsolvable problems are. Where you ask the medicine people, when do you think computers will take over doing things like people do? It's like, well, they already took over in a sense because they see from their perspective how they're losing things to the computer. Even Google being able to now Google things is something that's easy. So, that's easy, and past was really hard. So
Mhm.
you each things you ask about and the problems that Jason was talking about, those are real problems and are hard to solve. And like from engineering point of view, we still need to solve them in many of those. But from other perspectives, some of the technologies that started in the 70s are already in our cars now. So now the question is how do you close the gap and how far you reach to the point that it's becoming like common sense that we just go into the car and drive. So you can look at it pessimistically and optimistically. Look at it from both directions.
Yeah, I think there's also, an economic consideration, right? I mean, like look at trains. Trains are a much easier problem, but we still don't have autonomous trains. And the reason is just because the conductor does a lot of different things, and also the conductor doesn't necessarily cost that much money. You don't need that
Jason,
many conductors.
yeah,
Yeah, go ahead.
Jason, can I just break in and say there are autonomous trains in the world? I think it's economically they're not viable here because trains are a economically challenged industry as a whole.
By the way,
Sure, that's good.
shipping.
That's kind of where I was going with it, though. I mean, yeah, I think that, um, I mean,
Technically, it's been solved.
you could argue that the test track ride at Disney World is an autonomous car, but like, when will the autonomous cars be economically viable, right? And so, yeah, to your point, it's like in the U.S. at least, by and large, trains still aren't economically viable. So I think that getting the right business model is just as important as getting the technology right.
Yeah. So now I'll ask you the question the same way that Levi was asking. So it's like he made the bet against chess that he will win, and he did win. So let's ask the same question Andrew asked differently. Do you believe that next year driverless cars will you will be driving driverless car technology will get to the point that we won't need drivers anymore next year? Will you make this bet?
Um, it's an ambiguous question. I'll put it to you this way, right? I can go from the engineering office to the testing site via driverless car today in downtown Austin, right? So, you know, does that mean, can that same car drive in Dubai? No, it can't. In fact, it can only drive in downtown Austin, right? But, you know, so that's the problem, right? It's the operating, you know, the breadth of what the car can do is really that bar that's going to keep inching forward, right? And this is not uncommon, right? I mean, imagine printers, right? There was a time when you had to work for a huge company to have access to even a dot matrix printer, right? And so it's going to climb much the way that any other technology slowly climbs. But um, but again, it's really about finding the right business model. I mean, look at it this way: you can easily make a robot that can flip burgers, but the vast majority of McDonald's franchises still use human cooks, right? Even for the burgers, like you could just automate the burgers if you wanted to, but they don't, right? The person has to flip their own burgers, right? So that when people say how long until you buy an autonomous car with your own money and you have an autonomous car that's just dedicated to you 24/7? I think my answer is, a long time from now. And again, it also depends on how much risk as a society we're willing to tolerate, how much of the self-driving car risk. I mean, someone made this argument on Hacker News that basically if as soon as self-driving cars harm less people than human drivers, we should just swap everyone over. That's a really interesting philosophical argument, right? Because if you just look at it in terms of pure, reducing harm nationally or globally, then it makes sense. But it kind of breaks down because I might be much lower risk than somebody who makes who drives, let's say, a sports car and really likes drinking and driving or something. So it's like I feel like as a human, I can use my agency to reduce my risk, and so my risk might be a lot lower than the mean risk of the nation. And so my personal risk might go up a lot, even if we reduce the total number of fatalities, right? So that argument kind of breaks down, that argument that we just need to reduce the worldwide number of car fatalities. Then there's a cost issue as well, right? There's certain cost challenges around. There's certain even just like philosophical questions around if your car is a robot, why would you even own it, right? So there's a lot to work out there, and I don't think that. I feel like people who enjoy driving their car, don't worry, you're going to be driving your own car for the rest of your life. It's just this is a technology that's going to get better and better, and you're going to be able to use it when you want more and more. But I don't see cars going away anytime soon, like human-driven cars.
Okay. I would love to continue this discussion, but we're way away from Network X. So unless someone has like Python related questions, we're going to just stop the recording, but hang around here. Is it okay with everyone? Or if anyone has a Python related question on Network X, ask it now, please. Questions going once? Questions going twice?
Well, before we cut out the recording, just wanted to thank everyone for listening in, and hope you all out there try Network X. It's a really cool library.
Thank you.
Yeah, thank you for showing it to us. And I would like to thank you all. You all have like those clap thingies. So please clap, make some noise, unmute yourself just to make how you were happy to see this. So please, yay! Oh, you can see how people are happy. So I'm gonna stop the recording now.